Okay, guess we're going to start. Thank you for coming. I know 3 seminars in a week is a lot. My presentation today is going to be a mixture of the history of the work and why we started with this project, the motivation, how we plan it, and then I'm going to focus on 2 main scientific results, the regional heat transport and MOC, and the pathway of the MOC in the Southern Atlantic. But again, over there also we're going to have some new results, work in progress, and a summary of why we're doing this. This is something that we've been saying for a long time, that it's good to remind us why we're doing all this. The South Atlantic, the only basin extended to high latitudes that transport heat towards the north. And therefore, we know that there is a unique role in the energy balance that is played by this transport. So it has to send the upper water to the North Atlantic to compensate for the deep flow flowing along the coast. For many years, it was supposed, okay, we just measure what's in, what's out, but we know that that's not the case. In the paper that we published with Ricardo Matano, we analyzed the model, and we were able to establish that the South Atlantic is not just a passive ocean. Many things happen in the interior. Mostly, there are water buses, transformation, and creation. For example, in the 2 main regions where the energy is higher, like in the Brazil-Malvinas confluence or in the Cape of Good Horn over here, there we can see that this is these are the water masses, these are the levels, and this is how it's changing. In this one, in the number 1, we see the formation of the Atlantic intermediate water over here, and how in the Cape Basin we see that, on the contrary, that is going up to intermediate and surface water. Now, most of that waters are formed and transformed in the Atlantic, but also the Atlantic is an ocean that is open to the Pacific and to the Indian Ocean. And these 2 figures, I just put it here because I love the Argo flows, how they're doing. And this is an Argo flow that was launched in April of 2005, then through the Drake Passage in the loop, and here is in the Atlantic. And this one, it shows, started in 2010, but it shows the trajectory of the water at the level of intermediate water. And so it's open to both oceans, and as such, these places are choke points for one of the largest currents, the Atlantic Southwest Current. So one of the issue here is not the relative importance of the sources, but it's about the mechanism of entrainment, how are they entrained for both oceans, and what happened once they get into the Atlantic, how it interferes with the circulation. And this is why we cannot just say, okay, what's coming comes out. We need to understand what's going on. Another big reason for the studying this area is the paper that St. Keith published in 2011, in which he demonstrated using the NCAR model, one of the NCAR models, that the South Atlantic overturning circulation and heat transport explain the warming of the North Atlantic. And it's also that it's very important to know the passages, because this is how the sea surface temperature is affected. So this is very briefly the reason why we believe that the ability to understand and quantify the South Atlantic northward flow, as well as interocean exchanges and the pathway, is crucial if we really want to be able to have models that can forecast weather environment. We have a first famous meeting in a beautiful place that was Estance in Argentina in 2007. And the objective of this meeting was to gather scientists that have interest in the region, to start planning cooperation, and to start posing the main questions and define an observing system. It's an international project. We have Argentina, Brazil, France, South Africa, and the U.S. And in the U.S., NOAA and CNAS are the main players. This is where we are today. After 7.5 years, we were able to establish a pretty good observing system with new observations and based on existing observations that are related to what we want to do. In first place, there are the Cliver and Woes lines that are collected once every 10 years, more or less, at 30 south and 20 south. This is the U.S., this is the British. We have a high-density XBT line that runs between Cape Town and Buenos Aires, and this is done approximately 4 times a year. It's AX18. AX25 is running from Cape Town to Antarctica and back. AX22, and this is, Lamont has a line of current meters there. In addition to that, we were able to establish boundary current arrays. The Western Basin is maintained mostly by the U.S., Argentina, and Brazil. And what we have is a line of inverted echosonders. We have an ADCP over here, and we have repeated CTD sections. At the eastern side, we have more instruments over there. They have PIs and CPIs and ADCPs, and I don't know if you know that, but when I say PIs and CPIs, I think Chris explained it on the other time, an instrument that measures the integrated, it's a measure of the dynamic height. And we have acoustic Doppler current meter, we have toy moorings, we have shelf moorings. The eastern boundary is far better covered than the western boundary, but we don't need to give up, and hopefully we will get some additional moorings that we need in that side. Since 2008, we have 30 South Atlantic entertainment cruises, which is very good. 2015, we did 2. We have 2 more confirmed, and 1 we are suffering to get a ship to do it. But in principle, in addition to that, we have 142 high-density XBT sections and Argo floats and altimeters. This is an example of a SAM cruise, basically to show that with Argentina and Brazil, they are doing repeated sections. Hydrographic, LVDCP, sometimes they measure oxygen and other properties from the coast to the shelf, to the continental shelf, and they study the interaction, ocean, deep ocean, shallow deep ocean interaction. And the CTD lines continue on top of our moorings, Brazil and the US. Just to show you an example, this is the work that Alberto Piola is doing. This shows the sea surface temperature and associated with the Malvinas, the cold water of the Malvinas current coming from the south, the warm waters of Brazil current coming from the north, and this is a region of very energetic because of the front that is moving back and forth. So on purpose, we move the array further north to avoid all this motion over here. And with this section, we are sure, and this is also from Alberto, we are sure to capture all the water masses from the coast to the deep ocean. And we can see here, for example, the North Atlantic deep water, that is what's coming from the north at the lower limb of the NOC. And the Atlantic intermediate water is the one going up. Okay. Until very, very recently, I would say 10 years ago at the most, the values of the meridional heat transport in the South Atlantic were all over the place. The values were ranging from minus 0.23 to 1 petawatt. There were some estimates from sea-air fluxes, inverse models, some direct measurements of those CTD lines that I mentioned that were part of both and numerical modeling. The numbers non-consistent all over the place. And the reason was very clear. There were no observations there. So it was practically magic, okay? If you look at this picture that Gustavo gave me, we are missing here the CPD lines, that is a one realization. Not only the South Atlantic, but mostly the Southeast Hemisphere was a desert in what concerns observation. There was absolutely nothing here. So how do they get those numbers? Or the models, how well forecasted they were, hard to believe. But over here we can show 2014, and I'm sure this year we have more. The lines that we are running, next to the line I showed you before, plus all the other data, means that now we can do something with this data, and we can try to constrain the numbers and see what we have. For the meridional heat transfer over here, we started to do many different estimates. The first one that we did started in 2007, and we used a methodology that Molly developed for the North Atlantic, and we applied to AX18 this line. And these are the time series of the meridional heat transfer and the MOC in a further from petawatt obtained from the beginning, 2003 to 2015, when we started running this line. There is a very strong correlation between the two variables. These are 42 times transect values. And we obtain a value for MOC, in case that someone doesn't know, is the integrated transport and the upper layer until it turns around 1800 meters. And the meridional heat transport, you need to know, in addition of the volume transport, you need to know the thermal structure to be able to get the heat going through that section. And definitely, you need a close line from coast to coast. You need to conserve mass or salt or whatever you want to conserve, but it has to be close. So the relation is that an increase of 1 investment is better in the transport of the MOC increase and an increase of 0.047 petawatt. After that, there were a couple of papers that we published that basically, just as the first series that we have. Recently, Chen-Fu and Gustavo published a paper with the estimates that they obtained from the altimeter. The time series started in 93 to present, but I'm showing here only a little piece of it, the part in which they compare with what we obtained from the XBT. The numbers we are going to look at are all together, but again, I have about 19 and 0.5. And as you see, there was a pretty good correlation between the altimeter derived and the other one. Another product here at AOS2 in the same is from a product that Claudia and Susie developed for the Caesar Fahrenheit from Argo float, and they use altimeter sensor for it. So again, we have time series of those with numbers pretty similar to the others. This is from the CPI, when in the original work that we did using the very one CPI that we have in the eastern boundary with the ones that we have in the western boundary, like a difference in pressure and dynamic height, etc. So that's the very first estimate that we obtained. Currently, we are working in doing this much better, but now we have more data. And this is when it was published in 2013. These are the time series, and the blue lines are the values that we obtained with the XBT that we use for comparison. There are plenty of modeling results. I'm showing here only two. The one that René did when we started designing the observing system. So we were estimating what can be measured and how. And this is how this is the last one that I know. I know that there are two more here in the division that is the Brazilians. They are doing a part of kind of using HICO. So we can compare the results. And in principle, if you look at the observation, we more or less have all the same values. and it's not surprising. From altimetry derived and altimetry would flow most at absolutely almost the same angle for MOC, and it's because it's two different ways of getting data from the same source, more or less. Not for the heat transport, with the flows is higher, but we are all in the same range, more or less. What is different, and it's something that we have to take into consideration, is that this is a number we can say the way that we did this work, not the one that we're going to do now. We didn't have the mean because we didn't have pressure gauges at the bottom, so we can estimate the mean. So the mean comes from a model. Where do you get the boundaries? In the IS with the XVP, yes, the XVP cross the line. Argo flows, we know they don't go shallower than 1,000 meters. And altimeter in the boundaries also have to flow. So we need to combine all these observations to obtain a good value. And yesterday we had a meeting that was called by Molly, and we are going to try to work all together to make a good comparison that is not only showing the picture, and see how can we all work together and get the best estimate possible. Now, what is SAMOC providing? This is something that is important. We do not have the boundaries. If we want to close the sections, we need to close the boundaries. And SAMOC is going to provide the boundaries in both sides. The Argentinians are doing this project that is with Brazil, the two of them that they cross all this section along the coast, but mostly repeating the one that is the one at the edge of ours, is over here. And we're going to get all the values from the eastern boundary from France and South Africa. So no matter what methodology you use, you're not going to have to use a model to estimate the western boundary or some sporadic data that we might be able to provide a better value for that. So this is in what respects the meridian anti-transport. And now I'm going to talk a little bit about the pathway of the SAMOC links in the South Atlantic. And as I said before, we need to know the pathway in the South Atlantic in order to understand how the fluxes are distributed and what is the climatically important properties that they're carrying. Just to give an idea of this is the basic. The compensating flows is the North Atlantic water coming from the north, going out of Africa, the South Atlantic central water and the Atlantic intermediate water coming from the south of Africa to compensate, and this is the MOC in the South Atlantic. Now, the upper limb has been much more known, well known if you want. For years, the South Africans have been working hard. It was published an enormous amount of papers on Agola's fringe and the leakage. When we call it the leakage now, Lucho Hans didn't call it the leakage. There were many, many works done here. We also did some work. The first one that called the first more attention to this is when Arnold Gordon published this paper, Agola's ages in the South Atlantic. That's when geosat came up. So he was able to trace with the altimeter geosat, I'm talking to you many years ago. That was in 1990 that they published it. And he even got to the point to say, oh, and I'm pretty sure that this is going to get to the coast and some of the streams are going to be passed on the very right. Okay, yeah, Arnold, we'll see. But he was right. we're getting there. So the other push that we got to this was the paper that, it was the thesis, I think, of Donald, but Dryhouse was his advisor, in which they used the Ocan model, and what they did is they traced backwards the particles. They launched particles in the model, but they traced it backwards. So they saw that the water that was coming to the north was coming from the leakage. And in this diagram here, it's showing the percentage of the water that is going to the North Atlantic is like 80%. So another big issue was when Nature published this paper from Besta, in which he said that how the Indian Ocean water invading the North Atlantic. So now we not only have the rains, but we have the salt getting into the South Atlantic. It's a lot of things that can go on. And he finds out that due to the increase in the westerning, the number of rains was increasing. So the main thesis was that the additional Indian Ocean water that started to get into the Atlantic has to have a direct impact in the MOC. With a much less flashy title with Claudia, we studied the intermediate water flow from the south of Africa to the continent of South America using Argo trajectories. We find this. I think that Claudia published other papers after that. And this slide is from Sabrina Spike from France. This is the thesis of one of his students. He's tracing the Agulhas ring with altimeter, and you can see the difference of what can be done today and what Arnold was able to do in 1990. This is all more or less done, and this was well known, but now we have a project funded. René is the main PI with Ricardo Matano from Oregon State and myself. And in this, as part of this project, in a model that Matano has, that is Combetan Matano, this is a regional model in which he called the parent grid, and they have a child grid over here. So in this child grid, that it has a better resolution, what he's doing is injecting traces to follow the path. So the idea is that they're running the model, and then here we are going to look at the product, and we're going to interpret the results, comparing with all the data that we have. From the 20 years of this run simulation, this is a snapshot of here in this line. They launch a passive tracer that injected in the Agulhas core. And this is for the surface. It's between 0 and 500 meters. And in this square over here, you can see the time series of the upper water, because it goes to 500 meters here. This will be the deep western boundary, the North Atlantic deep water, and this is the deep water. And to how do you do this? Okay, hold on a second. And here we have a movie that I'm not going to show it all, but it shows how in the model, when you put those tracers, how they expand into the Atlantic Ocean and how the water, the Indian Ocean water, gets into the Atlantic, even faster, gets to the other coast, and starts mostly bifurcating. So we've been discussing this with Matano, and obviously there is no water going to the north, so 0 to 500 meters is not a good one. We have to do it again, including the intermediate water. That means it has to go deeper. It has to go to 700 or 1,000 meters. But this is the kind of thing we're trying to do now. The lower limb was less studied. And the reason was that in 2004, 2005, there were these papers published by Fritz Schott and Dengler, and they have an array of colorimeters, they have a mooring, they have a model, and the results were that when the North Atlantic water came from the north and they reached the Mid-Atlantic, they reached the Victoria Trinidad Ridge, they break into rings. And first, the topography here starts breaking into rings. And then when they reach the Victoria Trinidad Ridge around 20 south, it's only an eddy field and they disappear. However, we knew, because it was observed, that there was North Atlantic deep water along the coast of South America. And this is an example also that we published in the paper that shows in one of the south sections recently ventilated water that is characterized by high levels of oxygen over here in the coast that indicated the presence of the North Atlantic deep water. And also, this is a very preliminary result too, in which with no mean we show the variability as a function of time of the transport of the deep western boundary current at 34.5 south. So as part of that project that I just mentioned, we decided to conduct an experiment in which we are going to use all the available data that we have and two different products of the office model to define the pathways of the deep western boundary current in the Atlantic. So we think that that way we could better understand the physics and improve the strategies. This paper is being published now, right now. So as I said, we started with observation and evidence, and I'm not going to go too far with this observation and evidence, but I'm going to tell you that we know the characteristics of the North Atlantic deep water. We know the low temperature, high salinity, high level of oxygen. We know that it flows between those two density lines, and that can be traced with CFCs or other traces. So the lower limb is this that we are going to be following, and in principle, if you go to the atlas, the New Atlas, and the atlas was for the South Atlantic, and you look at the picture, you see that this is, here are the lines, okay? 11, 20, 30 south. At 11 south, you see the salinity and oxygen characteristics of the North Atlantic deep water. When you get to 20 south, over here, it's restricted to the boundary, and over here it's even more restricted to the boundary. Same thing for the oxygen. And then there is this line that crosses. And when you get to 22.5 here, you can see that there is some indication of the water. There was also the work done by this one in which he looked at nitrate, silicates, and CFCs, and he also concluded that around, in the middle of the basin, around 25 degrees west, that is over here, they show traces of the North Atlantic deep water crossing the Atlantic. But in the work that we did, I'm not going to show all the details, but let me explain what it is. This is the map of solution, and the map, the contour lines in the back are the CFCs 11 is a tracer, contours of that show levels of CFCs associated with the North Atlantic deep water going along the equator over here. We always knew that was here, and moving south. And we can see it around 25 north, 25 south, and along the shelf. This was done, the data, this map was done with data collected in 92 to 97. Now, with the new era data of Clymer, which I'm not showing you the data, but you want to see it here, we not only saw it 20 years afterwards, 20 to 30 years afterwards, not only was observed here, but it's observed here and here and here. So for the first time, we observed traces that indicate the North Atlantic deep water crossing the Walvis Ridge that's over there. Another thing data set that we analyzed is the Argo data. Claudia did a product that is a three-dimensional product. And so we send that and we use that to trace by, you know, that the Argo flows not only get the temperature and salinity, but they drift at a depth of 1,000 meters. So in the product that Claudia reproduced, there is a three-dimensional field of velocity, temperature, and salinity. So we estimated the velocity, or the velocity vector, at 2,000 meters, which is the upper area of the North Atlantic water. And it's clear over here that we have the main flow flowing along the coast, and then there is another flow that goes into the basin. Now, at least with the Argo flows, it gets very complicated here around 20 south, which is the latitude of the Victoria United Reach. And to be sure that this is still going there, we look at the sections of velocity along this line. The result is that, yes, it's crossing the Atlantic, but with very narrow jets. There are very narrow jets going back and forth. And this is why it's so more difficult to distinguish over there. The flows became more stable after they closed the Mid-Atlantic region. We use two products of the model. The first one is Sanseville and his collaborators did an experiment in which they launched in the office model flows at between depths of 1,000 and 3,500 meters along 5 degrees south. And the grid expands in this region. With that, they studied, basically, that's what they did, and these were mostly, what was the pathway that the flow took from South America to South Africa. And they explained, they find that that's the pathway, that's the main pathway of the water, and that it's right underneath the Angola Range passage. That means on the surface we have the Angola Range, and then you have this passage underneath. And the theory of what the delta they developed is that the decay of the rings, they form a tilt that change the southward velocity across isolines, and so while they go in a way, they are moving the flows on the other way, and that's why this transfer of water happened right underneath the Angola Range. So we asked him the product, he gave it to us, and we collaborated, and we did a different way of looking at it. We trace the flows. No? We start tracing the flows, backward and forward, okay? Tracing the flows from the model and then backwards, like, for example, where these flows come from. We trace it back. And so we find two main pathways, one along, this is just an example, because if we plot all the flows, it's a mess. So this is just an example of a few of them coming along the coast, making a jump at the Victoria United Reach because of the coastline, and the other one crossing the Atlantic. Now, this is the Lagrangian experiment we did. Then we look at an Eurasian analysis. We look at U and V and C and S, etc., and we estimated speed and kinetic energy to determine, also to verify the passages and try to explain what's going on. These two panels are the speed, I think it's 1,700 meters and 3,000 meters. This is the North Atlantic deep water upper layer. This is the lower layer. So we see, I forgot to say in the previous one, that of all the flows that were crossing 5 degrees south, most of them, 90% of them, were flowing south. There was a big recirculation, but flowing south, where 90% of them were west of 30. So it's all accumulated here, knowing the rest. So we have a strong deep western boundary current flowing along the continental shelf that then gets to the Trinidad Reach. We see very well in the upper layer, and we don't see it. Here it's not so clear, but still visible. But when we look at the epigenetic urgency, that it gives you a measurement of what's going on, here we don't see the crossing of the equator, but here we can see that there is epigenetic energy showing the two basins. So what happened one more is that we created a movie, we animated the flow, and we saw that the main motion was like a westward propagation across the basin. I'm not showing the movie, but this is, you can see this propagation. And this propagation has characteristics of the Rossby wave, that with velocities about 5 to 7 centimeters. These are Hoff-Muller diagrams. This is the time, and this is 5 east to 45 west. I thought I had one more, but okay, might be next. Also, with the Eulerian product, we estimated the transport of the 14 vertebrates that cross the Atlantic. Almost all of them is concentrated on the western boundary. Here we have some recirculations, and we have a point force going down. But most of the transport is along this basin, with recirculations that change the flows, for example, from 9 to 9.5. And about 4 highest vertebrates coming over here. With the Lagrangian analysis, I think it's here, we compare the numbers that we obtained with the Lagrangian estimates. These are Eulerian and Lagrangian, okay. And we compare with every piece of data that we can put our hands on. And so we see that the transport at 5 degrees south between the neutral densities that are the lowering are very similar when we did it with the Eulerian. And when you go deeper, it's very different, and it's because the data that goes 1,000 to 3,500 meters gets more water than the deep Atlantic, North Atlantic water. But in general, we have pretty good agreement with the numbers that we estimate with the model and the observation. So let's see what we can conclude for that. The first easy, straightforward conclusion is that the North Atlantic water follows 2 pathways, south of 5 south. The main pathway, we got 31%, is southward, flowing along the coast of South America. A small portion flows towards the interior. Approximately 14 vertebrates crosses 5 degrees south, but most of it is concentrated west of 30 west. And this flow breaks into rings along the coast of South America, where the flow is mostly non-stationary. Over here it's mostly rings. And this ring-dominated flow continues up to the Trinidad Ridge over here. So let's see what happened at the Trinidad Ridge. At the Trinidad Ridge that is here, preservation of potential velocity, vorticity, makes the flow, it makes the branching of the flow. So one flow continues to the interior, the other goes back. And about 20% of that flow is crossing the Atlantic into the interior. The remaining flows move along the coast, and a hypothesis is that, 2 hypotheses, that the Rossby waves are helping to get this, restore this flow against the coast. That's one thing. And the other thing is that the motion of this rings towards the interior has to do with those narrow jets that we mentioned before. So we have 2 hypotheses here. The first one, that the southwestward spreading of properties are a result of a combination of the eddy thickness flow, like Vance DeVille and his colleagues determined, enhanced by the clearly highly energetic eddy field at the Victoria Ridge and eastward jets. So we think it's a mixture of both things, that the fact that the decay of the Garzoli rings, but it's entrained also by this eastward jet. And the other motion, that is the one that is continuous towards along the coast, it is hypothesized that this westward propagation interacting with the mean circulation field might be the reason why south of the Victoria's Inner Ridge, most of the flow returns to the continental shelf as a more steady flow. No? It's a more steady flow that is the main branch of the deep western undercoast. So those are hypotheses. Now, the next step is have this model, we have the product, they can conduct, they say they can because I can, they can conduct more experiments to try to first determine if what we're looking at the same from the data is true, and we are going to analyze. First, we are going to validate the products of the model, and then we are going to try to analyze it to see if we can explain the things that we saw. For example, I know that Ricardo has a student that is looking in particular at the Sussex over here in the Victoria Inner Ridge, where we have all flows. But the first thing that we can say is that if you look at this line over here, where we have with the Argo flows on those narrow jets, well, the model has the same thing. And this is how the dye that it was put over there in the north is flowing towards the South Atlantic, 45 minutes, and moving along the south, the continental shelf, gets here to the Trinidad Ridge and starts branching. Most of the flow comes south. I'm going to make it faster if I can. No, it's getting to it. But as you can see, this is 20 years, okay? In 20 years, we didn't reach the other side. So this may need to run longer because we get to the Mid-Atlantic Ridge, and we didn't get the other part of the coast. And I think that's all that I have. And I said 45 minutes to start. We have 2 left. Thank you. Okay. Yes.
So the idea ahead for the deep west undercurrent is that would resurface in the South Atlantic and then kind of close the AMOC loop resurface in there. So do you see something like that going to the surface, or?
Yes, you see that it was. Wait. Oh, I got the wrong map. Sorry. Over here, there is a recirculation. That's the one you're talking about?
Yes.
Okay. You see that we have 9 quadrants and 7.5? There is a recirculation over here. And there is part, you can see, this one was from another paper. Yes.
But can you track some of the flows to the surface?
We have a transformation to the surface in a part of it. It's the one that I showed in the first, I think it was one of the first slides. Before the one, oh gosh, sorry. Okay, here we have the creation of the intermediate water, okay, from waters from the surface and this is in the western boundary, in this region over here. And this is where the Atlantic intermediate water is created. No? That's it? Yeah.
All this data you have in Sandlock now, the age-old controversy of, Gordon and Wintoul about how much of the upper limb is net on water from the ocean versus American water. You must be able to say better what that is, right? So the upper branch of the MOC coming across 35 south.
Mm-hmm.
How much is warm group and how much is cold group?
We don't know yet. We have the instruments in the water, in the eastern mountains. The thermometers that we have.
No, I was thinking-
Oh, you mean about the MOV?
You have an MOC profile.
Oh, yeah.
How much is in the thermocline, how much is in our intermediate water? I was just wondering if, when I teach my classes,
No.
students, I still tell them we don't know yet exactly what the answer is, but you answered it.
Still true,
No.
but check back in a year or so.
Exactly. We will be able to say more, as I said, when we look at the data we have in the eastern mountains. That's the one you're referring to.
Well, no, I mean that, we know a lot of thermocline water comes in the leakage, but then it gets recirculated, and so what's the net,
Okay.
Stormwater flux dissipation versus, and same for the intermediate water.
Okay.
That's what always made it difficult.
I didn't.
Show LOC profile and density space, you could answer it, I think.
Let me see if I kept it here. I took that fact out of the talk because I didn't want it to make so long. I think I kept the slide at the end. What we did, no, I was thinking on the MOV that we did the calculations of full transfer, okay? We did the calculation of full transfer. We have negative and stable MOC across the base. We did that. But that's the most that we can do. And was against all the models. Until now, there is one model that agrees with a negative MOV. One. And that's all what we can do. I thought I took that out of the presentation. Sorry. Any other questions? Okay. So only now we have to do the intercomparison. Okay. Thank you. How do I get out of this? How do I get out of this? I want my memory. Okay. Hey, Gustavo, 44, eh?
44.
Yeah,
Very good.
44. You asked me 45. Thank you.
Did you stop recording?
Huh? 44.
Recording?
I'm going to stop right now.